All right, how's everyone? So, questions. Hopefully you turned in your homework. I'm going to stop accepting late homework because people turn it in and then we talk about it, and then an hour later I get homework from someone, and that doesn't seem fair. So if you did not turn your homework in, turn it in right now, and I will give you 5 minutes grace period, and then I'm not going to accept it after that. And even if you didn't finish it, turn in what you have, and that's better than nothing, for sure. So, questions on the homework? Still not really sure how to go about proofs. That's okay. It's an ongoing process of getting the hang of it. So really the thing to do is just try more and more of them. There's a ton of examples in the book. There's a ton of questions in the book. I usually assign the even numbered questions, but the odd numbered ones have solutions. There's a extra batch of bonus questions at the end of each chapter that has more questions from each section in the chapter. And so those are all good ways to get better at doing proofs, but it's struggling with it. It's, sometimes not succeeding, and then after you've really worked it, seeing a solution to it. And that's what the odd numbered questions can help you with, right? Now, if you look at the question and you go directly to the answer, you've lost the possibility of learning from that question. But sit down and really work it. Try it a bunch of different ways. Take a break, come back, try it some other ways. And then if you're really stuck, look at the solution. And then go on to the next question, but repeat that process. Try it a bunch, and so on and so forth. And let's go through some of those right here. So let's see. Let me go to the homework. This was homework 3. So I will post homework 4 after class. And that's going to be some more proofs, probably related to even and odd numbers, so things that we've already done and already seen and talked about. All right, last chance to get homework in. 5-minute grace period is up. All right, so that is closed. So let's go through some of these. Would you go over 3.5 number 6? Not sure what to do next. Structure as a proof didn't look like the others. 3, 5, 6. Okay, let's 3, 5, 4C and 3, 5, 6. Okay, let's take a look at these. So 6 is struggle with wording. Yeah, it does not look the same as the others. That's okay. The only thing you missed was some discussion about how to do proofs, and that I'm not accepting late homeworks anymore. So question 6, determine the validity of the following argument. So it's going to ask you to either prove this or come up with a counterexample. And this one is weird because of the way it's worded. It can be confusing. So the statement says, for students to do well in a discrete math course, it's necessary that they study hard. Students who do well in courses do not skip classes. Students who study hard do well in classes. Therefore, students who do well in discrete math do not skip class. So it's not clear if when they talk about doing well in discrete math, how that relates to doing well in courses. But I think the interpretation here is if you do well in courses, you're going to do well in discrete math, right? Because that's a course. So I don't know. Let's just write some propositions, and let me move this out of the way, and I'll read from it. For students to do well in discrete math courses, it's necessary that they study hard. So let W be the proposition. Student does well. And I don't know if we have to specify that as discrete math versus all courses, but we'll come back and clarify that if we want. So W is the proposition that student does well. Let S be the proposition that a student studies studies hard, studies. And then we are told students who do well do not skip classes. Okay, so let's C be the proposition student skips classes. Alright, so for students to do well, it's necessary that they study hard. Okay, so this is a conditional statement, but we got to be careful about the condition. To do well, it's necessary that you study hard. So to do well, it's necessary that you study hard. That doesn't mean that if you study hard, you will do well. That's really saying, right, if you do well, then you know that you studied, because studying is necessary for doing well. So this is really saying W implies S, unless I'm getting confused again. There's a 10% chance of that. If you do well, it means you studied hard. That's the same thing as saying it's necessary to study hard in order to do well. But it doesn't go the other direction, right? In order to do well, you must be breathing, right? So if you did well, you know that you're breathing. But knowing that you're breathing doesn't mean that you're going to do well. So it's not the converse. All right, so everybody okay with that for the first statement? Students who do well do not skip the classes. So now we're being told if you do well, you do not skip classes. Students who study hard do well in courses. So if you study hard, you do well. So now we've got an equivalence, right? Therefore, students who do well do not skip courses. And this is where it starts to feel really goofy, because we've already got a proposition saying that that if you do well, you do not skip courses. Well, it was our second proposition. Students who do well in a course do not skip classes. And the conclusion is students who do well in discrete math do not skip class. I think that follows because that's this proposition. So it seems to be that the conclusion we're asked to prove is just a restatement of a hypothesis. Is there some other way we can interpret this that makes it more interesting? So did anybody take this? So discrete math versus courses. So we could make this more interesting as follows. So let D be the proposition do well in discrete structures. Let S, what did I use before? S be the proposition you study hard. Let's see. You study hard. Let's see. Be the proposition you skip class. And then let's make a general proposition. W be the proposition you do well in classes. So D is the proposition you do well in discrete structures. W is the proposition you do well in classes in general. Any other specification that we need, and yeah, D will imply S. Well, no, S will okay. Any other specification we need? Discrete math, study hard, skip classes, do well, skip class. Okay. So now we can write down what we're told. For students to do well in discrete math, it's necessary that they study hard. So if you do well in discrete math, that means that you studied hard. So we've got that. Students who do well do not skip classes. So if you do well, then not C. Students who study hard do well in courses. So if you study hard, then you do well in courses. And what you need is a connection between W and D here. So if you do well in courses, then you do well in discrete math, because that's a course. So I think you need to add a fourth proposition, which is if you do well in classes, you do well in 215, because that's a class. And now you're asked to show that if you do well in discrete math, then you do not skip class. So you're asked to show that D implies not C. And that looks like a chain rule, right? D implies S, S implies W, W implies not C, therefore D implies not C. I don't think we needed that additional hypothesis either. So if you do well in discrete math, you study hard. If you study hard, you do well in classes. You do well in classes, you do not skip class. Therefore, if you do well in discrete math, you don't skip class. Okay, I think you got it then. So usually when I write questions like this, like for tests and stuff, I'll try to be very parallel structure in the statements I make. If you find something like this on an exam where it's not really clear, definitely ask. Don't just assume what I meant and then go forward from there. Ask a question. How are you grading our proofs? With a big red pen? No. I don't know. I mean, I'm going through them and I'm looking to see if everything you wrote was a proposition, and if the reason you gave for each statement is valid and follows from the things that come before. We have to type in proofs on exams, or will we be uploading PDFs? I have not completely decided, but my leaning right now is I'm going to have you upload a PDF, which means you can either type it or you can write it and do a picture. Either way. But these are doable in typed form pretty easily, right? I mean, you do this for an arrow, and you do this for an equals, and you do that for an and you do that for an or. and you can do that for not, and so on. But particularly this course, there's so much symbology with set notation and functions and summation symbols and all that I'm leaning towards wanting you to turn in PDFs and either typesetting it in a really clear way if you like typesetting formulas, or just writing it up and sending in a clean picture of each page as a PDF. We'll talk about that later this week. If you're going to use symbology like an exclamation mark for not, make really sure that you put a note right next to, the first time you use it, where you say this means not. Because you can use an exclamation mark, you can use a tilde, you can use a number sign or a backslash. There's all kinds of things you see. But yeah, just specify so that there's no ambiguity. All right, and then somebody asked about 3.5.4, question C, I believe. So what are we told? A or B, C and D. A implies not C, and therefore B. All right, so let's do a direct proof. So what's a general plan of attack for this? Did anybody find a good direct proof? Write down the hypotheses, okay. And then what can we put together? Or what new propositions can we write? Not A or not C. So you went to conditional equivalence. And then what do we have? Contrapositive of 3, so C implies not A. And then chain 4 and 5. Chain rule doesn't work unless you have two implications. Conjunctive simplification, which I'm guessing you want to use to get C. So we know C and D are both true, so in particular we know that C is true. And D is a red herring. D has nothing to do with any other statement in the question, so D is really just kind of there to confuse us. So now you've got C, and we know that C implies A, so we could use 5 and 6 together to get not A. And I can never remember the term the book uses. That is detachment. And if we know that A is false and A or B is true, that gets us B. And that's, what is that? So, false or B. Right, that's just A is false, so if false or B is just B. And that's what we're after. Yeah, disjunctive simplification. Thank you. So how do you know that these are the steps? Well, you don't. You experiment, right? So we didn't actually use conditional equivalence. There might have been another way that we could do this without, you know, that would actually use this step. But you're kind of grasping in the dark and just trying different things. And when you grasp the right thing and it moves you forward a little, right, your brain starts forming patterns, right? It starts looking for, well, what was going on when I grasped for that? And what was not going on the other time I grasped for something, and it didn't lead to something fruitful. And eventually you start to develop this kind of intuition for, you know, for me, like I see a negation and I see a C and I get excited. It's like, oh, maybe I can put those together somehow, you know. But it's just kind of trying different things. It's puzzle solving, you know. All right, so let's do the indirect proof. So we've got A or B, C and D. A implies not C and B. So let's start off with A or B. And I'll just write down all the hypotheses. So that's a hypothesis, hypothesis, hypothesis. And then we'll negate the conclusion. And we'll if you feel like you're getting stuck in direct proofs, just negate the conclusion and make sure you use it. If you negate the conclusion and then you completely ignore it and go on and prove B and then say that contradicts not B, that's where you haven't done an indirect proof. You've done a direct proof. So make sure you use this negated conclusion. Well, how can we use not B? There's only one other proposition that includes B. That's a disjunction. And we can again use disjunctive simplification. Right? B is false. A or B has to be true. A must be true. So that's 1 and 4 combined together to give us A. And then A implies not C, but A is also true, so that gives us not C. And that's detachment again, 3 and 5. And conjunctive simplification gives us C. And there's our contradiction. So we've got C and not C. Those can't both be true. That's a contradiction. Therefore, our negated conclusion was incorrect. Therefore, B must be true. And that's what we were asked to show. And this is the quandary of physics students worldwide throughout history, right? You see a problem worked out, it makes sense. You sit down and try to work out a problem yourself, it doesn't make sense, right? This drove me nuts when I was in school. I'd like go to the recitation and I'd ask questions and I'd watch the teacher work out, 10 different versions of problems, and they all made absolute perfect sense to me. And then I'd get home and I'd open up my book and I'd work on the first homework question and I'd be stuck. It's like I have no idea what to do with this, right? It's frustrating, but it does help to see problems worked out, but only if you intersperse that with struggling, right? And trying to find solutions. And it really is just an exhaustive search sometimes. I mean, we have, you know, this collection of possible things we can use, and some of them we're not going to even bother with, right? We don't have any conditionals. We're not going to mess with any of these things that involve conditionals. Or we don't have, you know, A implies B, B implies C. We're not going to use the chain rule. But, you know, we just tried different ones. Maybe we should, you know, take P and Q and just change it into P. Why? I don't know, because we can. You know, so you try to do the things you can and see if any of it gets you any further. Sometimes it makes it more complex. If we start doing too much, you know, disjunctive addition, we can end up with more and more confusing propositions that don't actually help us. But it's strictly trial and error, and you will figure it out over time. And if you don't figure it out, you know, in this class, that's okay. This is not like a deal breaker, right? It's all stuff that's going to help, and the more you get this and the deeper you understand it, the more helpful it's going to be to you down the road. But you know, it's stuff that you're going to have your whole life to figure out, so don't stress over it. And it's, you know, one part of the course, but a lot of what we're going to be doing in the course is not going to be, you know, writing things like this, but we're going to be using the same ideas underneath a lot of other stuff. Alright, yeah, and someone says they write out lots of stuff and then they make a more consolidated proof later. That's a really good strategy to follow. Work on a big sheet of paper, scribble, change your mind, go back and start again, draw arrows, that kind of thing. And then when you've got a pathway, now try to go through and write it up cleanly with just the essential steps in the right order. And then you can turn that in. Alright, cool. Other questions? I think I accidentally left steps I didn't use on my homework. That doesn't bother me at all. If you leave steps off, that's a bigger problem, because then it's not clear if you knew how to get from, you know, from here to there. But if you have extra steps that don't lead you anywhere, that's okay. I'm fine with that. That's just showing me, you know, your thought process. That's actually even better in some cases. All right. Well, I will try to get these graded by Wednesday and get them posted with some feedback. What if I didn't write the names of the rules that rules used? Just thought that made sense. The justification for each step is a critical part of the proof. If it's really, really obvious, I'll probably be okay with it. But unless, you know, it's you know, like the last two statements being put together in some obvious way, yeah, you really need the justification for each statement. Otherwise, you're asking the person looking at the proof to recreate the proof, basically. So yeah, always put the reason next to each statement. Yeah, the book can do all kinds of things, and you know, sometimes when I'm teaching, I'll be doing something really fast, but in general, right, you have a step number, you have the proposition, then you have a justification for it. I'm sure they don't do that a lot of times in the back when they're listing the answers, though. Can we know what number you'll be grading for this? I don't know. Good chance I'm going to be grading the proofs, so I'll probably be grading some set of questions from 3.5 question 4. I don't know if I'll grade all 6 or if I'll you know, do one direct and one indirect, or what exactly. But I'll see what I got and go from there. Again, don't panic though if this is not, you know, crystal clear to you. I mean, the homework grade is a small part of the grade, and it's really not there to, like, you know, weed out the people who are going to go on and the people who aren't. It's really there to give you an opportunity and a framework to work on this stuff, and to take your best shot, and then to get some feedback on you know, what's right and what's not quite right, and then you know, work more on that before the exams. Now the exams are really there to you know, assess where you are in the course and stuff. The homework is, you won't believe me, but the homework's really for your benefit, right? So work on it hard and take it seriously, but don't stress over it if you can. All right. Well, let's continue with divisibility and division and things like that. So we had this notion, this terminology. A vertical bar B, and that's a proposition, which says A divides B. So this is something you could write as a line in your proof, right? Now we can't write, you know, A times B or A divided by B or A plus B. Those things are not propositions. But this is absolutely a proposition. It's the proposition that B is divisible by A whole number of times. Okay, but it's not a mathematical operation. It's a proposition. And we talked about the division algorithm, which said that if you take, let's just think about positive numbers for a moment. If you take a number B and you take another number A, we can write B as, you know, some multiple of A plus some remainder, where that remainder is between 0 and A minus 1. And we're going to use that to talk about modular arithmetic. And so we had this idea of if we fix a number like A, right, and so I'm going to assume A is a positive integer here. If we fix a modulo A, we could take any integer and equate it in some way with the remainder when you divide that number by A. So we can think of these as modular classes, right? A way to take the set of all integers and break it into a small set of, a small collection of sets. So for example, if I work modulo 3, I can write any integer and I can equate it with its remainder when I divide by 3. So what do I get when I divide 0 by 3? It goes in 0 times with a remainder of 0. So here's an integer, here's the remainder when divided by 3. If I take 1 and divide it by 3, what's the remainder I get? 1 divided by 3? Get a remainder of 1. And 2 divided by 3, oh, I messed up my beautiful picture. 2 divided by 3 is a remainder of 2. If I take 3 and I divide it by 3, I get a remainder of 0. If I take 4, I get a remainder of 1. 5 gives me a remainder of 2. 6 gives me a remainder of 0. 7 gives me a remainder of 1, and so on. So every time that we take a number and we divide it by 3, we get a remainder that's either 0, 1, or 2. So we can take this infinite set of integers and reduce it to one of 3 values, where that value is the remainder when you divide the number by 3. And another way to think about this is we can take the numbers and break them into 3 groups. For example, all of these numbers have the same remainder when we divide by 3. They have a remainder of 0. All of these things have a remainder of 1, and all of these things have a remainder of 2. All right, and then I mentioned at the end of class on Friday that the idea was we were going to take questions about, potentially very large integers and reduce them to questions about much smaller integers by moving from the space that we're normally used to working with into this much simpler space with just a few integers that are usually really small numbers. And we'll be able to do things over here in this simpler space that will tell us things about operations in this much larger infinite space. So this is modular arithmetic. And so new terminology. And for all of this, let's fix some moduli m. So usually whenever we're working on these things, we're just going to have a fixed moduli in mind. Minus 5 divided by 3, is that a remainder of 1? Good question. So I think it's negative 1 with a remainder of 2. Well, let's write it out. Negative 5 equals something times 3 plus something. So negative 2 times 3 plus 1. Yeah, so the remainder would be 1. All right, so still confusion, or cleared up now? So technically you could use negative 2, but we're always going to try to find a remainder between 0 and the thing we're dividing by minus 1. But technically, right, this is negative 5 equals negative 2 times negative 1 times 3 plus negative 2. So there's also a remainder of negative 2, right? But we're trying to find a remainder that's either 0, 1, or 2. The negatives are weird. So don't worry about the word remainder. Let's just use a formula. So we want to write, so the remainder when A is divided by D is the number, a number R, such that A equals some quotient times D plus R, where that's an integer, right? We're trying to write this number as a multiple of D plus something left over. So remainder when A is divided by D, we've got A, we're going to write it as a multiple of this plus something extra. So for positive numbers, this is usually not confusing, right? A equals 7, D equals 3. We can write 7 equals 2 times 3 plus 1. So that's the remainder. A equals 5, D equals 3. We can write 5 equals 1 times 3 plus 2. So that's the remainder. But with a negative number, we do exactly the same thing. A equals negative 5, D equals 3. Negative 5 equals what? 2 times 3 plus 1. Sorry, negative 2 times 3 plus 1. Negative 5 is negative 6 plus 1. So that's the remainder. And if we're looking for a remainder, generally we want that remainder to be bigger than or equal to 0 and less than the thing we divided by. So in this case, we want R to be bigger than or equal to 0 and less than 3. So it's either 0, 1, or 2. That's the three options that we have. All right, cool. Negatives are always strange with this, right? But come back to this, right? Think of it as, you know, your number is something times the divisor plus a remainder. But, you know, it is true that a remainder of negative 2 is also correct, right? We can say negative 5 is negative 1 times 3 plus negative 2. That is a remainder that you get when you divide by 3. It's just not a remainder that, you know, falls in this range. Cool. All right, so some more terminology. Fix some moduli m, so the divisor, right? We're going to fix what we're dividing by. So we say A is congruent to B modulo m. So we use that triple equal sign again. It's not logical equivalence now. It's a totally different operation. A is congruent to B modulo m. That's what this says. If A divided by m and B divided by m have the same remainder, A is congruent to B mod m if when you divide each of those by, you know, m, you get the same stuff left over. This is why we want to know what the unique thing is that something is congruent to. Okay, so some examples. Let's just stick with 3, so let's work modulo 3. So 7 divided by 3 is 2 with a remainder of 1. 22 divided by 3 is 7 with a remainder of 1. They have the same remainder, therefore 7 is congruent to 22 modulo 3. This is exactly using the percent sign in C, right? All right, this is all you got to know about modulo stuff, right? Everything else flows from this. Right? Two things are congruent if you get the same remainder when you divide them by m. So 7 is 1 more than a multiple of 3. 22 is 1 more than a multiple of 3. They are congruent. So somebody give me a number other than 15 that 15 is congruent to mod 3. So 3 is a good one. 30 is a good one too. 6 is a good one. Right? Because 15 when you divide by 3 has a remainder of 0. Well, 3 divided by 3 has a remainder of 0. 30 divided by 3 has a remainder of 0, and so on. 5, however, when you divide by 3, you don't get a remainder of 0. You get a remainder of 2. But what could 5 be congruent to mod 3? Right, 5 would be congruent to 8, for example. Okay. And it would be congruent to 11. And it would be congruent to 2. Because 2 divided by 3 is 0 with 2 left over. And by the way, 15 is also congruent to 0. Because 0 divided by 3 is 0 with 0 left over. And by the way, 5 is congruent to 5. Because 5 and 5 have the same remainder when divided by 3. Kind of obvious, right? What about 7? So 7 is congruent to 4. 1 more than a multiple of 3. 1 more than a multiple of 3. 1 more than a multiple of 3. Right? Because 9 is a multiple of 3. This is 1 more than that. 12 is a multiple of 3. This is 1 more than that. So all of these are congruent to, actually, 1. And 16. And we're not dividing into 0 pieces, so we're not doing modulo 0. But we can take 0 and divide it into 3 pieces, and each piece is 0. So 0 divided by 3 is a thing, but dividing something by 0, not a thing. And all numbers are logically equivalent to positive and negative infinity too, right? So yes and no. So if infinity were a number, we could make statements like that. But infinity is not a number, right? So infinity divided by 3 doesn't work. It's not an integer. It's a notion of something bigger than any integer. But if you divide an infinite set into 3 pieces, each set 3 equal pieces, each set is still infinite. So in that sense, yes. All right, so we have this modulo operator. It lets us know if two things are modularly equivalent by asking, do you get the same remainder when you divide by the moduli? And there's a few things. So yeah, modulo 0 would be we can't modulo by 0 because modulating by 0 to say that 7 was congruent to r modulo 0 means 7 equals some quotient times 0. I was hoping that would look more horrifying than it does. Yeah, just don't do it. Yeah, it looks like a remainder of 0, but I don't think that's right. Yeah, that's weird. That should look more horrifying. So 7 mod 0. So I guess technically if we were to do mod 0, everything would be congruent to itself. But that's yeah, try not to think about it. We're never going to want to do things modulo 0. So here's the real issue. When we do this, we want a number that's bigger than or equal to 0 and less than the thing we're dividing by. Right? So to find the thing that A is congruent to, we want to find some r which is bigger than or equal to 0 but also less than 0. Right? And that's just strange. Alright, so is this okay so far? Just thinking modulo 3, looking at some positive numbers here. We could throw in some negative numbers, but I'm not going to do that. We'll do some negatives later, but we can do plenty with just positives. So these are just the remainders when you divide by 3. And you notice some things about this. First of all, every number is congruent to itself. And that's kind of gotta be the case because, you know, the remainder when you divide this by 3 and the remainder when you divide that by 3, well, since they're the same thing, you're going to get the same remainder. We also notice if A is congruent to B, then B is congruent to A. Again, because, you know, the remainder of this and the remainder of that is the same as the remainder of that and the remainder of this. I mean, if these are the same, then those are the same. It's almost a silly statement. What's a little more interesting is this. There's transitivity. Right, 5 is congruent to 8 and 5 is congruent to 11. Well, that right there tells us 8 should be congruent to 11. How do we know that? Because the remainder when we divide 8 by 3 is the same as when we divide 5 by 3. And this says the remainder when we divide 11 by 3 is the same as when we divide 5 by 3. Well, if this is the same as that and that's the same as that, then these are going to have the same remainder. So everything that's written in here is all congruent to each other, and 3 and 30 and 6 and 0 are all congruent to each other, and so on. You specify the mod usually by, in parentheses, writing parentheses mod and then the moduli. So 15 is congruent to 3, parentheses mod 3, close paren. Alright, so still good. Alright. So I'm going to call this a fact instead of a theorem, or a factr. A is congruent to B modulo M if and only if M divides A minus B. So two numbers are congruent modulo M if and only if M divides their difference. And if you go back to here and you look at some of the numbers we found that were congruent to each other, the difference of any of these is always a multiple of 3. 13 minus 1, 13 minus 4, 10 minus 1, 13 minus 10. Each of those is a multiple of 3. 30 minus 6 is 24. 30 minus 3 is 27. Each of those is a multiple of 3. 11 minus 5 is 6, multiple of 3. 8 minus 2 is 6, multiple of 3. So basically, any number is congruent to any other number if its remainder after using the modulo function is an integer including 0. Not necessarily. A number is congruent to any other number if for each of those numbers, the remainder that you get is the same when you divide by whatever your moduli is. So 10 divided by 3, I have a remainder of 1. 4 divided by 3, I get a remainder of 1. That's why these two are congruent to each other. But an equivalent fact is these things will be congruent anytime that their difference is evenly divisible by M. And this is a key fact we're going to use. And this is pretty straightforward to show. Why is this? If A is congruent to R modulo M, then we can write A as some quotient, let me call it Q1 times M plus this remainder R. If B is also congruent to R modulo M, then we can write B as some other quotient times M plus that same remainder. Right? This is the definition of what it means to say that A divided by M has a remainder of R. It means A is some multiple of M plus this remainder. B is some possibly different multiple of M plus the same remainder. Well, if we know this and we know this, then we can write something about A minus B. That's Q1M plus R minus Q2M plus R. And if you get rid of the parentheses and do the math, this is just Q1 minus Q2M plus 0. In other words, the difference of A and B is a multiple of M with nothing left over. So M divides A minus B. So if you don't like algebra, plug in numbers. Right? Do this. with some more interesting moduli and some interesting numbers. All right, you ready to start building on this? Probably not. That's a good sign. All right, so some facts and things about modular arithmetic. Let me just start tossing out some theorems here. We're not going to delve into the detailed proofs of these things. We're not going to give these fancy names and refer to them. We're going to use these, but let me state some of these things as theorems, just to make the statement that like these are, you know, actual things. But then we're going to start using these, okay? So I'm not going to keep writing mod m in parentheses. I'm just going to write it once for the whole page here, okay? If A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D. What does this mean in practice? Here's two things with the same remainder. Let's call that remainder R1. Here's two things with the same remainder. Let's call that remainder R2. If I add A and C, I'll get the same remainder as when I add B and D. In particular, when I add C and D, what's my remainder going to be? R1 plus R2. Okay, let's try this. Mod 3. So 17 is congruent to 11. Right? Why is this true? Because 17 is 2 more than a multiple of 3. 11 is also 2 more than a multiple of 3. So 17 is congruent to 11. 10 is congruent to 100. This is 1 more than 9, which is a multiple of 3. This is 1 more than 99, which is a multiple of 3. Guaranteed this is true also. In other words, 27 is congruent to 111. And in fact, both of these are multiples of 3. This is 3 times 37, this is 3 times 9. Yeah, that is weird. This also works for multiplication. A times C will be congruent to B times D. So I know automatically 17 times 10 is congruent to 11 times 100. So 170 and 1100 have the same remainder when you divide by 3. That's where it starts to get useful. Because I don't want to divide this by 3. I don't really want to divide that by 3 either, but that's a little easier than that one. But you know what else you can do? $17 is congruent to 2. Right, it's 2 more than 15, which is a multiple of 3. 10 is congruent to 1. It's 1 more than a multiple of 3. So 17 times 10 is congruent to 2 times 1, which is just 2. Is the star in AC times BD? Yes, thank you. Congruent to. Thanks. Okay, so what just happened here, right? 17 is congruent to 2, 10 is congruent to 1, so 17 times 10 is congruent to 2 times 1. 170 is congruent to 2. So I know right away 170 is not divisible by 3. I know 170 is 2 more than a multiple of 3. But I didn't actually do any division. I did a really tiny little bit of math over here. I multiplied 2 by 1. But it told me something about this. Since 17 times 10 is congruent to 1100, I also know that 1100 is congruent to 2 modulo 3. Right, 1100 divided by 3, it's 366.66666. That's 2/3. That's the extra 2 left over. So this is the kind of stuff we're going to start doing a lot of. And it's going to be fun. Will it work with square roots? Oh, square roots get interesting. Where'd the 2 times 1 come from? Uh, 17 is congruent to 2, 10 is congruent to 1. 17 times 10 is congruent to 2 times 1. That's what this says. That's okay. All right, so what this means is if we fix a moduli, we can do addition and multiplication before or after we find a modular equivalence. So for example, 64 is 1 more than a multiple of 3. So 64 to the 5th power is congruent to 1 times 1 times 1 times 1, 1 to the 5th power, which is just 1. So this number is going to be 1 more than a multiple of 3. And it takes no work. So there's the number in question. Divided by 3, and you can see we've got a little bit left over. It's 1 more than a multiple of 3. We didn't really have to do a whole lot of work to get there, right? Because we know 64 is one more than a multiple of 3, so 64 to any power is actually the same as 1 to any power. So I could do 64 to the 10th. I could do 64 to the 100th. That's a big number. But if I divide by 3, I'm guaranteed it's just one more than a multiple of 3. Alright, so our game plan now is we're going to work in this different arithmetic system where if we fix a moduli m, we're only going to deal with integers between 0 and m minus 1. But if we only care about remainders, if we only care about what something is congruent to modulo m, we can do addition and multiplication before or after we reduce to this class of remainders. So if I want to find 64 to the 5th, I could multiply this out 5 times and then divide by 3 and see what the remainder is. Or I can start with the remainder and multiply that out 5 times. Is that making any sense? Say again?
Could you repeat that one more time?
So the game plan is we're going to fix a moduli, and when we want to do arithmetic on numbers, we can do the arithmetic first and then find what the remainder is. But we can also take our numbers, change them into their remainders, and then just do our math on those remainders themselves. And these are always going to be small numbers, right? In this case, numbers that are either 0, 1, or 2. Whereas the numbers we start with might be really large. So we're going to do calculations involving large numbers, but we're going to work on their remainders instead. And it's going to be much simpler to work over here because the numbers are easier. And there's going to be really large problems that we want to solve that we can actually do by hand. Or maybe with a pocket calculator, even though we might be dealing with something that has, 10,000 digits in it, which our pocket calculators won't do, we can still answer questions about arithmetic operations by first changing them into these remainder classes. And because of this, right, we know we can do this for addition. We know we can do it for multiplication. We can also do it for subtraction. And subtraction is really no different than addition. But division is a tricky matter. And square roots are a tricky matter, which someone asked about a while ago. There's some cases where we can do those things, but we're going to talk about when we can or can't in a little bit. But subtraction is pretty straightforward. But let's play with this. We've got a few minutes. Let's pick a slightly more interesting moduli. So let's look modulo 7. And so what's 2 plus 2? Well, it's just 4. 2 plus 4 is just 6. What is 2 plus 6 congruent to modulo 7? I mean, we know 2 plus 6 is 8. But what's 8 congruent to mod 7? It's also congruent to 1. And our goal is going to try to find, congruences bigger than or equal to 0 and less than 7. So generally we wouldn't stop with 8. We'd say, okay, but there's also something it's congruent to that's less than 7 but not negative. That would be a 1. So it's also 15. but we're going to have this kind of preferred number, which is between 0 and 6. So what is 2 plus 5 congruent to? That's a big old 0. Because 2 plus 5 is 7, and 7 is divisible by 7 with no remainder. Well, when we first think about negative numbers, so, here's a number 10, we're asking 10 plus what gets us back to 0. And whatever our answer is here, we call that negative 10. Well, we just found something that when we add to 0, when we add to 2, gets us back to 0. So maybe we should call this thing negative 2. What do you think? Would that be a weird thing to do, or would it be cool? Both. Good answer. It is a weird, cool thing to do, and it's totally legit. Because guess what? 5 is congruent to negative 2 modulo 7. How do we know that? Because negative 2 can be written as, you ready for it? Negative 1 times 7 with a remainder of 5. That's negative 7. You add 5, you get negative 2. So we have a way to represent negative numbers. It's the thing that when you add to the original number gets you back to 0. This, by the way, is where 2's complement comes from. This is why 2's complement works in Engineering 250. Because if you take a number, the 2's complement is the thing that when you add it to the number, you end up with 0. Now you get there through the funny business of complementing each bit and adding 1 or moving in and toggling the first non-zero, etc. But that's where it's coming from mathematically. So we can definitely add, we can subtract, we can multiply. Division will be a different matter. But here's a fun exercise, since I haven't posted homework yet, but I will. Try to make a multiplication table. Modulo 7. And then try to make a multiplication table modulo 6. It's good practice at finding modular equivalences, but it's enlightening. And we'll do this in class on Wednesday, and we'll compare these, and this will lead us to a discussion about division and what it means to divide, and that will also take us into some of our next topics in number theory, which is prime numbers. So do that if you feel like it. If not, we'll do it in class Wednesday. All right, have a good one. I will see you next time. Thank you.